Thanks a lot. I'll try to make you learn something because this is the last talk of the day. The topic of the talk is exploring decision tree for thematic map creation. And I'll start with giving a bit of background on why we want to do this. So if you think about how to create thematic map nowadays, how it's done, broadly you have two different options, right? The first option is you are a programmer. You can use languages like R, JavaScript, or Python. And usually this is coupled with libraries like Leaflet or MapLib or sometimes D3.js. So that's the first option. I'm a programmer and I know how to program things and I can do it. But on the right-hand side, you can see a second option, which is I can use a tool, and there has been kind of suggestion of toolkits actually. And what they do is, basically you upload a data set, and then based on the feature, the characteristic of the data set, then the tool automatically suggests for you what is a meaningful map to create, either a choropleth map, graduated symbol map, and so on and so forth. So this approach has advantage because you don't have to be a programmer to create your map, but the disadvantage is that you don't know what works under the hood. Why is it that at the end of the day I got a choropleth map or let's say a heat map suggested as an option? And this is what we want to try to address. If you want a general keyword, is more in the area of explainable software. We want a user to understand what the system is doing. Now, if we take for granted that okay, the system should be able to explain, there could be three benefits. So one thing is transparency, explain the logic of the system to users. The other possible benefit could be education, help users to learn how this system works. And then the third advantage could be scrutability, which is if you are an expert, then you are enabled to tell the system whether it is wrong. Now we work with the premise that the decision tree is the brain of the software. It is the logic behind everything that is being done. So it is quite important to see how we can communicate this with others. Now, we said we want to explain decision trees to users, but now the question is, why do we use interactive 3D scenes? And here you can have a look at the literature from learning. And what we know from there is that 3D is not beneficial every time for everyone. This is not the case, but when 3D is beneficial, the benefits is usually higher level of engagement or additional exploration possibilities. Likewise, interaction is also not beneficial every time for everyone, but when there is benefit, the benefits are increased attention, curiosity and interest. And so we thought, okay, then let's do interactive 3D so that we have basically the two benefits that could be useful in this context. We looked a bit into related work. On the left-hand side, what you can see is 3vs.net. So it is a platform where the author has collected all the possible ways of visualizing decision trees. And when you filter by the dimensionality, which is 3D, what you obtain is you have 67 results, but none of these things was addressing the problem as we wanted to. On the right-hand side, you have open source software, scikit-learn, matplotlib, or the Graphies open source software. These are all software that are helpful to visualize decision tree, but they are usually tailored to the context of machine learning, but not broadly applicable. So the main goal of the work is to foster knowledge sharing around software for automated thematic map creation. So we want to help developers to share the knowledge about how this software works, and we want to help developers also to communicate to users how the software works. And we had done this exploratory work to learn about the merits of the 3D 4DT approach, which I will present in a minute. But before I do so, a word on decision tree. What do we really mean by a decision tree? At the end of the day, it's a rooted graph with a conditional statement at each node. And now you can think about, we basically divide the decision tree into two categories: explicit decision trees and implicit decision trees. Now let's pick this one. It is a picture that is taken from a book in cartography, which is when do you create which type of maps. And what you can see, for example, is that if you have qualitative data, create a nominal map. If you have quantitative data, then there are some more ifs, right? And then you can create a choropleth map, or you can create a dot density map, and so on and so forth. So what you can basically see is this has a tree-like structure. That's why it's already called an explicit. But when I was trying to explain, I just used if-else, which means that basically this can be converted also into a graph-based structure, and this, which I won't. I mean, we did it in the paper, but I won't say more at this point, can also be converted into this. Now, the approach that we propose try to answer two questions. Is how to represent these decision trees that we have seen as machine-readable data. And then the second one is how to automatically generate 3D scenes from that machine-readable data. So basically, we take this thing, which is actually a picture available somewhere, and then we try to to encode this as a JSON format, and then from there is an automatic process to generate the scene that is appropriate, and then that helps user to navigate. Now let's pick the first part of the story, which is a representation. What we propose is a controlled vocabulary. We have basically 6 terms. We have 3 types of nodes and 3 types of edges. I'll go through them quickly. You have a root, which is a node without a parent. That's basically this guy here. You have a leaf, which are nodes without children. This is these guys here. And then you have inner nodes, which are neither roots or leaves. Then you have edges, which connect nodes, right? So you have parameter, which connect a root and an inner node, superclass, 2 inner nodes connected, and then meaningful, which is connection between an inner node and a leaf. And if we pick the example, for example, this relationship here is labeled as a parameter because it is one of the parameters that tells us which type of thematic map to create when. This relationship here is called meaningful because it tells us when it is meaningful to create a nominal map, or this one will tell us when it is meaningful to create a choropleth map. And then we have a superclass, which is basically documenting the hierarchical relationships between the different things. So we had this controlled vocabulary, and then this is what we use actually to encode all the decision trees that we had as JSON format. Now, when we finish this, then there is a question of how do we build the scene automatically. Then you need a mapping from the node elements to the user interface elements. Root is not mapped to anything, but leaves are mapped to cube. So when you have a leaf, then this is mapped to a cube like this. We tried with spheres, but it didn't end up to be convincing, or especially when you want to display preview pictures, so we switched to cubes and kept them. The inner nodes are mapped to radio buttons. This is the type of thing that you see here. The parameter, they are mapped to sections, geometry, data type, and then the superclass, we can see it on the map. This is basically in the background, and it's just the same for the meaningful thing. Then I think I will show quickly an example. So we created the whole thing using open source software, Node for the backend, 3JS as a library, and then we use Vite.js for the front end. And I will quickly show the demo. So what you can see here at this stage is that we have different options. You can upload your own decision tree. Upload your own decision tree as a JSON, or you can use one of these pre-prepared. So we have encoding some examples to start with. And then the upload happens. And when this happens, basically all the different leaves that are in the tree are selected. So we are trying to see a preview of all these things. So these are all the different options. Now, when the user starts to play around with the different constraints, what happens is that there is a highlighting mechanism to explain which of these things are more meaningful, and which are not. So the bigger ones are meaningful. Now, one thing that can also happen is that you can get closer to one of these cubes, and by that you can get some more information about what the type of map is, and that continues then for the rest. And I think I will just stop here at this point. Yeah, so that was a prototype. Now the question is, how do we evaluate the whole thing? So we again divided the evaluation into two parts. One of the parts was a representation. How expressive is the vocabulary that we have created? And this is what we did. So we picked all the three examples that I have shown before. Maybe I can come back. We picked all these three examples, and then we encoded them in JSON. This is what you can see here, and details are on the paper, or the encodings are on GitHub. So we're encoding all these things, and I think it works quite nicely because it supports this type of decision trees. And one thing that is nice with the encoding is JSON is that even if you don't want to go to the next step, which is the interactive 3D scene, you can use existing software to already know what your decision tree is about, and this is what we have been doing here. Now the next thing is, okay, how usable is the whole thing for the user? And this is what we did. We did an experiment. We had two conditions. And the third condition is the 3D 4DT prototype. And then in the traditional condition, what we did is we took text and picture and built a website. And now we ask the user to interact with both options. So you interact with the interactive 3D scene, and then you also interact with the picture and text. What we measured is how fast they were, how accurate they were in answering the questions, and explicit memorability. So we told them at the beginning, okay, you will interact with the decision tree. They explain how the software works. But remember that after the interaction, or after the section, we will close. After we close the session, we will ask you some question about what you remember. That's why we call this explicit memorability. Now we presented, or we used these two examples. This one is an example of implicit decision tree. As we said, this one is explicit. And the second difference is that basically this one is much denser. So we have here graph density values. So this one is a much denser node than that one. And most importantly, this one is actually a decision tree that is using a prototype already. But here it's a decision tree that is taken from a book. Now, what the results say is that, in principle, both conditions perform quite well. There is no significant difference in most cases, but there are sometimes some slight advantages. So the 3D condition was a bit slower, but that is expected because this is the new condition. And what we can see is actually the 3D condition had a better effectiveness rate, so people could answer questions better using that, and also they could remember a little more when the prototype was closed. Now looking more here, it's according to the type of decision tree, then you can basically see that it is with decision tree B that the whole approach is much more beneficial. And then if I come back, decision tree B is this one. It has a quite neat hierarchical structure compared to this one, which was a bit more complex. So the whole thing was a bit of an exploration, so to see if that is an approach at all that can help user navigate the logic of software, and because it has promises, we can basically say it is something that on the long run, if we improve, could contribute to visions of design transferability. So you can just think about documenting the logic of the software as JSON once, and then because it's JSON, then there are many different software that can visualize. It doesn't have necessarily to be a 3D. Now, from the communication point of view, it is the same thing that we have said. It's a way of fostering algorithmic transparency and enabling sharing of functionalities across systems. But what we have noticed is that memorability is still an area that we can work on, because it dropped basically from 80% to 40% after the completion of the experiment. Yeah, so I think this is the last slide. So we have different ways of creating thematic maps. There are tools that help us create this thematic map automatically, but these tools do not explain to people how they came about the results, and this is the type of problem that we want to address. We propose here to use a controlled vocabulary to encode the logic, the decision trees of this software as JSON, and then a way of automatically building interactive 3D scenes. The evaluation showed some good results. Now, in future work, we want to go beyond thematic cartography because there are other places of free open source software that could be interested in this thing is spatial analysis. So how do you explain to user why some spatial analysis method has been taken in one condition or the other one? The other thing that we want to test is the learnability, because for now we are the one encoding the decision trees as JSON, but the question is, if a cartographer would be given the whole vocabulary, how can he proceed with this? So this is learnability. And then the whole scalability, how many of these cubes can you create it at max, and what is the impact on performance? I'm done, and I'm curious to hear about your questions.